Our next topic is the study of nonlinear equations and how to solve them. And we're going to find a surprising connection between solving nonlinear equations and using linear approximations to do so. Let's start off with things that we might already know how to solve, though. For example, here's a quadratic equation, and I think most of us would be pretty comfortable recognizing that this is factorable. If we add a 4 and subtract a 1 here, we would get 4x minus x, or 3x, and so we could solve that pretty easily. X equals negative 4 and x equals 1. If either term is 0, the whole thing is 0. Okay, so that's pretty easy, if you know the skill. Here's another equation, 10e to the negative x equals 7. We've seen these a little earlier in the course. We need to solve for x, so how do we solve for x? Well, we have to isolate x. We can get in closer here if we bring the 10 to the other side. And then, of course, we need to get this x down to the main line. So we take the ln of both sides. Ln of e are inverses, so we end up with negative x equals ln of 7 over 10. And so x is equal to negative ln of 7/10. If you're feeling fancy, you could also bring the negative inside and make that ln of 7/10 to the negative 1, better known as 10 over 7. That's totally optional. At this point, you could put it into your calculator and get a value back. Okay, we're doing all right. We know how to solve nonlinear equations. How about this one? Oh, it's almost the same as the last one, except there's a plus x here. Okay, so let's try the same thing. Let's do 10e to the negative x equals 7 minus x. E to the negative x is 7 minus x over 10. Bring the 10 over. Then we can do ln of both sides. And then we get negative x equals ln of 7 minus x over 10. And we start to realize there's a problem. This x, the one we're solving for, that we want to get x equals, it's also here on the right-hand side. We haven't gotten rid of it from there yet. And, well, kind of like here, we could have written, I guess, x equals 10e to the minus x. That would be negative plus 7. Saying x is equal to that doesn't help because we don't have it in terms of numbers only. We have it still in terms of x. In fact, if you look at this, the fact that there's an x in the exponential and one in the main line here means we can't solve for x by hand. There's no amount of manipulations with lns and exponentials that will let us solve for x equals. Can't be done. And yet, we should be able to find a solution. There is a solution to this. If I plug in some numeric x value, I can make the left and right-hand side both equal 7. We just don't have a strategy yet for how to do that. Okay, so I want to reinforce this message. There's a lot of relatively simple equations, just like the one on that last page, that cannot be solved by hand. And this may be a bit of a surprise, but if you think about it, in a math class, you would probably only be asked to solve equations you can solve. Otherwise, it's just frustrating. So we're now going to open up the gates and take a look at all sorts of equations that we can't solve by hand, and instead that we can find solutions for using numerical methods, which let us approximate the solutions. So that being said, what we're going to do is learn an algorithm that'll generate an approximation. The caveat around all of this is that it's never better to use numerical methods instead of by hand, if you can solve it by hand. If you can solve it by hand, you should, but otherwise numerical methods are something that you can fall back on. And the reason we don't like approximations that are numerical is that they are approximations. They're not an exact solution like ln of 10/7. And we also can't generalize a numerical solution. When you have an equation with some unknowns in it and you can find the solution in general, then it's something you can reuse. Numerical methods just give you one approximation for one example, and then if you want to do it again, you have to do all the work again. let's get into the practice first. All right. Here are the steps of the algorithm we're going to use. The first thing we're going to do is rearrange the equation. We're not going to change it. We're simply going to put everything on the left-hand side. Okay. And what we're going to do is call that f of x. So what we now have is a new version of the function, or the equation rather, that we could write as some function equals 0. All right. Graphically, what we're looking for is where the function crosses the x-axis, or when its y value equals 0. So if we plug in some values like 1, 2, and 3 here, we can get a number of y values that go with that. Just plug these in, round it a little bit for simplicity. And what we get here are values negative 2.3, negative 3.6, 3.5. Oops, that's minus 2, that's minus 3. 1, 2, and 3. We can imagine, without getting all the details, that the graph looks something like this. It should be fairly smooth, it's nice exponentials and x's, so it should look something like this. And what that tells us is that the solution we're looking for is somewhere in the range 0 to 1. X is equal to 0 to 1. Some value between 0 and 1 will satisfy this equation. So we'll just write that down. It's worth noting to ourselves, what property of the function did we use to actually make that statement? Well, we said if the function is up here at 3 when x is 0, and then it's down at negative 2.3 at x equals 1, somehow the function must get and cross the x-axis because f of x is continuous. The fact that we can only connect 3 and negative 2.3 here with a line that's unbroken guarantees that somewhere in between 0 and 1 here, we're going to cross the x-axis. All right. So adding a few more points to the graph looks like this, including the point at 0.5. So that seems like our closest approach to where the hypothesized graph is going to cross the x-axis. Why is that important? When we find an x that makes our function 0, we found a solution to the equation. All right, let's compute the derivative at the point x equals 0.5. Reminding ourselves of the function, 10 e to the negative x plus x minus 7. That means that f prime of x is going to equal minus 10 e to the minus x plus 1. And so at x equals 0.5, our derivative is going to equal, with a little bit of calculator work, around minus 5.07. And again, if we imagine the slope here, it's a half step, 2.5 is where we'd end up roughly. So that would be our tangent line approximation there. Okay. Next, we're going to zoom in. Notice the scale here. This is 0.5 here. This is the entire block from 0 to 0.5 zoomed in. And we're going to take our slope of about 2.5. Sorry, our slope of minus 5, which turns out to be about 2.5 difference on this interval. And we can see that the real curve, drawn in green here, is going to look an awful lot like the blue line, the tangent line. So this is the actual graph, and the blue line is the tangent line. And what we said earlier when we first introduced tangent lines was if we zoom in sufficiently on a graph, we're pretty zoomed in here, then the tangent line and the graph will look almost identical. And that means not only do they look identical, but they're going to share properties like when do they cross the x-axis. So we expect if we follow the tangent line back to the x-axis, it's going to be very close to where the actual curve that we're trying to solve for the x-axis intercept for is going to have its solution as well. All right. So would the root of the tangent line be close to the root of the real curve function? Absolutely yes. We have zoomed in, and the tangent line is a very good approximation to the shape of the curve. It's a very good approximation to the graph on this short interval.